Welcome. Today, we're jumping into the world of vector geometry. Now, you might think of this as just, arrows floating around in space, but it's so much more than that. It's really a powerful language that we use for everything from physics to computer graphics. Basically, it's how we describe our three-dimensional world. So, let's get started and break down what makes a vector so special. So, first things first, let's get a really important distinction out of the way. Some things in our world just need a number to describe them. Think about temperature or mass. Those are called scalars. But what about something like the wind or a push? Just saying how hard you're pushing isn't enough, right? You also have to know which way you're pushing. And that combination, a magnitude and a direction, that's the heart of a vector. Here's our roadmap for this explainer. We're going to start with the absolute basics. What is a vector? Then we'll build up our toolkit with some basic operations. After that, we'll bust out the power tools, the dot and cross products. And finally, we'll use all of that to actually build things like lines, planes, and even some pretty cool complex shapes. All right, let's jump right into section 1. What exactly is a vector? When you strip it all away, a vector is just an object with two key ingredients: a magnitude, that's its size or length, and a direction. That's really it. Now, they live in something called a vector space, but don't let that term scare you. It's really just a playground where all these vectors follow the same set of rules. The easiest way to picture a vector is as an arrow, but the math behind it is all about its components. In 3D space, that's just three numbers that tell you how far to go along the x, y, and z axes. Think of these components like the vector's DNA. They hold all the information about its length and the way it's pointing. Okay, so now we know what a vector is, but what can we actually do with them? It's time to open up the toolkit and check out the basic operations. There are really three fundamental moves, and they're all pretty intuitive. We can add vectors, which is like combining forces. We can subtract them to see the difference between them. And we can multiply a vector by a simple number, a scalar, to just scale it, make it longer, shorter, or even flip it around. Visually, this stuff is actually pretty elegant. When you add two vectors, it's like walking one path, then walking the next. The result is the shortcut from your start point to your end point. And scalar multiplication? That's even easier. It's like turning the volume up or down on the vector's length. And here's the best part. The math is surprisingly simple. You can forget about the arrows for a second. To add or subtract vectors, you just add or subtract the matching components. To scale a vector, you just multiply every single component by your number. It's really that easy. All right, we've got the basics down. Now it's time to upgrade to the power tools. There are two really special ways to multiply vectors: the dot product and the cross product. And trust me, they unlock a ton of new capabilities. Now, here is the single biggest difference between them, and you gotta remember this. When you take the dot product, the answer you get is just a number, a scalar. But when you do the cross product, you get a whole new vector as your answer. The output isn't just a value, it's another object with its own length and its own direction. So what does the dot product really tell us? Well, geometrically, it's all about alignment. It measures how much two vectors are pointing in the same direction. If you get a big positive number, they're on the same page. If you get a big negative number, they're pointing in opposite ways. It's a test of agreement. And this right here leads to its killer app. We know the cosine of 90 degrees is 0. So that gives us an incredibly easy test. If the dot product of two vectors is 0, they have to be perfectly perpendicular to each other. This one little trick is an absolute cornerstone of geometry. Now let's talk about the cross product. Its magic is that it creates something new. You take two vectors, u and v, you cross them, and the result is a brand new third vector that is guaranteed to be perpendicular to both of the original ones. It literally finds the one direction that sticks straight out of the flat plane that your first two vectors create. And if that wasn't cool enough, check this out. The length of that new vector isn't just some random number. Its magnitude is exactly equal to the area of the little parallelogram that your original two vectors would make. So the cross product gives you a direction and a meaningful area. How cool is that? So now we've got our whole toolkit. Let's actually put it to work and start building our world, starting with the most basic things we can make: lines and planes. So let me ask you a question. Think about it. If you had to define a perfectly straight, infinite line just floating in space, what are the two essential bits of info you'd need to lock it down? The answer is actually way simpler than you might think. All you need is a single point to start from, and a direction vector to tell you which way to go. That's it. The equation just says, start at this point and then travel some distance along this direction. By changing that distance, you can land on any point along the entire line. Okay, let's use the same logic. Now imagine an infinite flat sheet of paper. What two things would you need to define its exact position and tilt in 3D space? For a plane, you need a point that's on it and something called a normal vector. That's a vector that sticks straight out, perfectly perpendicular to the surface. And this is where our dot product trick comes roaring back. See, any vector that lies flat on the plane has to be at a 90-degree angle to that normal vector, which means their dot product has to be 0. That one rule defines the entire plane. But of course, lines and planes are just the start. The real power of all this comes alive when we use the same ideas to describe much more interesting curved surfaces. Once we start using squared terms in our equations, like x squared and y squared, we open up a whole universe of new shapes. For example, if all the squared terms are positive, you get an ellipsoid, which is kind of like a squashed sphere. But if you just change one little plus sign to a minus sign, the shape can radically change into something like a double cone. Or what if you have one variable that isn't squared but the other two are? Then you get a paraboloid. And this bowl shape isn't just some math curiosity. It's the exact shape used for satellite dishes and telescopes because it has this amazing property of focusing all incoming signals to a single point. And all of that is described by one clean equation. So everything we've looked at so far has been static, describing fixed shapes. But let me leave you with this question. What would happen if a vector wasn't fixed? What if its components could actually change over time? Well, then you're not just describing a location anymore. You're describing a path. You're not describing a shape, but motion. And that one simple idea opens up the door to calculus, physics, and a whole new way of describing our universe.